So then we have a force on the particle. The force which is acting on the particle in a magnetic field, if the direction of the motion of the particle is perpendicular to the direction of a magnetic field, it will experience a force which will cause a circular motion. So for this, we use a Fleming's left-hand rule. According to Fleming's left-hand rule, your index finger, your first finger represent the direction of a magnetic field. Your second finger represent the motion of the particle, which direction the particle is moving. And your thumb will represent the motion, the direction of the force. And all will be perpendicular or 90 degree to each other. Like example, if a magnetic field is towards right, so particle example going up in the magnetic field. So which direction it will experience a force? It will experience the force in Z direction. So all will be 90 degree to each other. So whenever we want to find the force on the particle in a magnetic field, we always use a Fleming's left-hand rule. And we apply the Fleming's left-hand rule for positive particles. If it is a negative particle, then what does it mean? It will move opposite to the direction of a magnetic, opposite to the direction of the positive particle. Example, so this is a region where we applied the magnetic field, and the magnetic field is into. And we have a particle which is entering perpendicular to the magnetic field 90 degree. Magnetic field is into, and say this is a positive particle, a proton is there. So you have to use a Fleming's left-hand rule. According to Fleming's left-hand rule, your index finger or first finger represent the magnetic field. So where your first finger should point, your index finger should point into. Your second finger represent the direction of the particle. We apply the rule for a positive particle. If it's a negative particle, then it move in opposite direction. So if we apply the rule for a direction of the particle, in this example, your second finger should point towards the right hand side. So first finger is pointing into, second is pointing towards right. Where your thumb is pointing? What is the direction of your thumb? Which direction your thumb is pointing? So it is pointing top of the page. So as a result, what will happen? When this particle will move, it will move in a towards the top of the page, or it will move in a circular path. And the direction of the force is continuously changing. Because it is moving in a circular path, whenever object move in a circular path, there must be a resultant force acting, and that resultant force must act towards the center. So when the particle enter, the moment that force was to in this way, but then as it is changing the direction of the force is also like relative direction is towards the center, but with reference to the magnetic field, all the position, the direction of the force is changing, like it remain towards the center. So idea is that whenever a particle move in a particle enter a magnetic field perpendicular, it will experience a force which cause a circular motion, or we can also say it will move in a curved path. What if we have a negative particle enter from the same direction? So if you have a negative particle enter the same direction, so as a result, what will happen? It will move in opposite direction. The curvature of the particle, curvature of the track depends on the momentum of the particle, the product of mass and velocity at what is the mass of the particle and what is the speed at which the particle is moving. So the curvature, if the particle is having a high momentum, it will have a like greater curvature is there, high momentum. This is a particle with a high momentum, and this is a particle with a low momentum. Momentum, the product of mass and velocity. So high momentum, greater radius of curvature, like greater radius of curvature means like radius of this curved path will be larger. And for an object which is having a low momentum, will have a smaller radius of curvature. If the paths are in opposite direction, it means the particles have a different nature. Is it clear the idea of force on a particle moving in a magnetic field? Any doubt in this? Then sometime the particle does not enter the magnetic field exactly perpendicular. In this case, the particle, like the direction of a magnetic field and the direction of the particle, it is 90 degrees to each other, because like magnetic field is into and the particle is entering, so the angle between them is 90. But what if the particle is not exactly entering at an angle of 90? Then it will have two components of the motion. So we have this region is a region of a magnetic field. And the particle does not enter exactly perpendicular, it is making a certain angle. So in this case, we have to resolve the velocity into components, horizontal and vertical. It depends on what angle is given to us. Like sometime angle with perpendicular is given, sometime angle with horizontal is given, but you have to resolve into component. So example, if we have the angle with this angle is given with horizontal, like theta is there, and this velocity is v. So the component of the v, there will be two components of the v. One is with an angle, so this will be v cosine theta. And this component will be v sine theta. According to the angle given angle, v cos theta and v sine theta. Or if the angle is given other way around, so we have example, this angle was given, and this was v. So we resolve into components. So component which is with an angle. So in this case, this will be v cos theta. And this will be v sine theta. So here v sine theta is perpendicular to magnetic field and v cos theta is like exactly perpendicular to the magnetic field, the component. So as a result, what will happen? What is the difference between this one and the previous diagram? The previous one, only like it is entering directly perpendicular without making any angle. Like there were no component. But in this case, we have the component. So as a result, what will happen? It will have a helical motion, like move like a helix, a spring. So it will have two components. One is causing a circular motion, like this one will cause a circular motion, and the other one will cause a downward motion. So how the particle will move? What will be the track of this particle? So it will move like this. One component is moving it down, v cos theta, and one component is perpendicular, causing a circular motion. So as a result, the motion of this particle will be helical, a spring, a spiral track it will follow. But if it is exactly vertical, exactly perpendicular, no component is there. So as a result, what will happen? It will just move in a circular path. Is it clear the difference between the two tracks for a particle in a magnetic field? Any doubts or a question? And if you want to calculate the magnitude of the force experienced by the charged particle, so we use a formula F is equals to BQV, where B is the strength of a magnetic field or a magnetic flux density. Q is the charge of the particle. and v is the speed at which, or the velocity you can say. But we always take a perpendicular component. Like whenever you want, if the particle, the always a perpendicular component to know the direction of the, like if you know the angle which it is making with the magnetic field, so you always take a perpendicular component of the velocity to work out the force experienced by the charged particle. So F is equals to BQV is used to calculate the strength of a force with the charged particle experience when it is moving in a magnetic field. And because in a magnetic field, whenever a charged particle is moving in a magnetic field, it always moves in a circular path. So when the charged particle is moving in a circular path, what will happen? There should be a force which is causing a circular motion. So we can say a centripetal force is there. So simply we can say the magnetic force which is equals to BQV must be equals to centripetal force. Centripetal force is mv square over r. So the magnetic, when object move in a circular path, the force which is causing a circular motion, that is a centripetal force. And in this example, the magnetic force is a centripetal force. So we can compare the two values. So we can say BQV or mv square over r is equals to BQV. So this B will cancel with one of the square, and Q will go there in division. So M over Q, the mass to charge ratio, is equals to BR over V. So we can use this formula to calculate the mass to charge ratio of different particles. So if you want to calculate the mass to charge ratio of the particle, uh, we apply the particle is moving through a magnetic field which causes circular motion. And when it causes circular motion, the ratio between mass to charge is equals to the strength of a magnetic field times the radius divided by the speed at which the particle is moving. So for a circular motion, we use this formula when particle is entering a magnetic field. This is the same formula just I write now. But the condition that force is always acting perpendicular to the charged particle, and the particle and the magnetic field should also be perpendicular. What if the charged particle is accelerating, like if we use an electric field? So purpose of the magnetic field is to deflect, and the purpose of the electric field is to accelerate the particle. So whenever we use a magnetic field, we use to deflect the particle. And whenever we use electric field, we use electric field to accelerate the particle. So if you use a magnetic field, so we have the formula, the magnetic force and the centripetal forces are equal. So centripetal force is magnetic force because it is causing a circular motion. So we use centripetal force is mv square over r, and the magnetic force is qvb. So we cancel with square. So we have m over q is equals to qb. Sorry, m over q is equals to b r over v. This formula we can use. We can find any one unknown. So if we have a magnetic field, the magnetic field will cause the circular motion. So we can relate the circular motion and find mass to charge ratio. And if electric field is there, the purpose of the electric field is to accelerate the particle. So we apply a certain potential or a voltage, and that causes a particle to accelerate. So the electrical energy will be equals to kinetic energy. So in this case, the kinetic energy of the particle will be equals to electrical energy. Kinetic energy is half mv square, and electrical energy is voltage into charge, PQ. So if we need mass to charge ratio here, so that is equals to 2V, but this V is not the speed, this is the voltage. This V is the speed. So this V is the speed and this capital V is the voltage. So it will be 2V divided by V square. So using this, we can also work out the mass to charge ratio, because mass to charge ratio is used to identify the particle. So using a mass to charge ratio, we can identify the particle. So if electric field is used, the mass to charge ratio is twice the voltage divided by speed square. And if magnetic field is there, then it is equals to BQ over V. Is it clear, this one? The two formulas? And we can also modify this. We can also modify this formula. Like according to this formula, the mass to charge ratio is BQ over V, where this V is a speed. Here, this V square is also a speed. So what we can do, if I work out the value of the speed here, in the magnetic field formula, it is BR over V, because Q I move in denominator and R I move to numerator. So mass to charge ratio is BR over V. So this V, if I want to work out this V, so this V will be equals to, this V will be equals to BR into Q divided by M. If I need this V, and like from this formula, I work out V and then I substitute it here. So when I substitute this formula, then we have the charge to mass ratio according to, like the final substitution, the charge to mass ratio, it will be equals to 2QV over M in a root divided by BR. This is a final. Why this formula is more useful? Because it's easy to measure the strength of a magnetic field, the voltage, the mass of the particle, and the charge. Like this include the constant values, like strength of magnetic field will be constant, radius, the charge will be constant, mass will be constant if the particle is not moving with a relativistic speed. So we can use this formula more effectively rather than the other formula. So this is also a formula to work out the mass to charge ratio. So this was about the charged particle, the magnetism. So unit 4, we are done with unit 4.